Thank you for having me here. It's quite a pleasure and an honor to be here about almost 20 years after we started that idea of aspect-oriented programming, which I have been sort of more or less looking on the sides at what every one of you has been doing. And the interesting thing is that some of those ideas, especially the more conceptual ones, not necessarily the ones that are more language-oriented, but more conceptual ones, some of those ideas, I keep coming back to them in different things that I do. And this is one of them. So I thought this would be an interesting talk to give here because a lot of what I'm going to talk about is probably a different domain that you probably don't know much about, but you will see things that I'm going to talk about that will sound really, really familiar. Okay, so these are all problems that kind of pop up over and over again because they are unavoidable when you're designing systems and large systems in general. So just to give you the talk is going to be basically, I'm going to show you some cool urban simulations, and then I'm going to talk about how to design them, okay? And just to give you a little bit of background, why am I doing this that seems so different from language design and so different from my PhD thesis of like 20 years ago. I tend to do lots of different things. And so one of the things that I've been doing over the past 8 years or so is I'm a core developer of an open source project that is sort of an emulation of Second Life, the server side of Second Life. For those of you who maybe have heard or haven't heard about Second Life, this is a massive multi-user online environment. It was very popular a few years ago, but basically it's like a 3D game. But what it has in particular is that people can, it's sort of a 3D wiki. People can build their own 3D models and give them behavior. So it's like a small talk environment on steroids and online and massive multi-user. So it's a really interesting environment. At the peak of its popularity back in 2008 or so, there were lots of people trying to find usages of this platform that went beyond just the pure socialization. And some of those people were people related to architecture and urban planning. And there was a very strong interest, especially for those people in that domain who are very close to politics and to governments and local governments, to find better tools to convey to the public the plans for urban redevelopment that are going on everywhere. So that's one of the major problems that they have is how to convey to the public what the real estate developers and the politicians want to do. So, so there was a lot of interest from the point of view that these environments are online, they can be accessed by people, and you know, there was a question, can we actually use this as a communication tool to present the urban redevelopment plans? And so since I started, you know, I thought that the platform and the engineering challenges of the platform were really interesting, even before I got involved in urban planning. So I started collaborating in that project, an open source project, and sometime later I was approached by some of these people that did urban planning, in particular in Sweden. Sweden is very much advanced in everything that has to do with virtual reality and 3D modeling. And so they started a business on precisely this proposition of doing 4D visualizations of urban redevelopment plans. Okay, and I went along to kind of provide the engineering side of it to support these environments for them to actually model. And it's very rewarding for me to see that it's a viable company. There's lots of projects that they're doing in cities in Sweden and some of them in the US. So that's sort of the background for why am I even talking about, you know, 3D virtual environments and what does that have anything to do with aspects, but I'll tell you a little bit more as we go along. So let me tell you about the domain of urban simulations and the problems that I found here. And this is, again, this is all things that I learned as I went along. I had no idea about any of this a few years ago. So one thing that became very apparent is that the people who do simulations, and in particular urban simulations, think of urban simulations as pictures like this. Okay, and this is not my picture. This is taken from a talk from a person who is very well known in the simulations world, Fujimoto. He's at Georgia Tech. But they tend to think of urban simulations as this overlay of aspects, right? Urban aspects being, you know, the water supply, energy issues, the community and social issues, parks and recreations, the buildings, financial activities, traffic, shopping, you name it. It's basically a bunch of aspects, okay? Some of them actually use the word aspects, okay? Sort of informal. And that's exactly what they are. They are aspects of a city. So this is one, you know, that's the first sort of connection with the idea that there's some interesting relation between you know, urban simulations and some of the conceptual ideas that we had here in the aspect-oriented programming. So just to give you even more concrete, let me show you a video of one of the models that this company does. I'll just let it play here. So this is Uppsala, for those of you who have been there. This is near the station. And this was so Uppsala is one of the earlier customers of this company, and you know, they were kind of planning or trying to visualize what it would take to deploy a tram system in the city. So Uppsala does not have a tram system, but the tram systems are coming to Sweden. You probably, if you've been to Stockholm, you've seen them already. So they were trying to visualize what does it feel to have a tram system deployed right at the station area, right? So we modeled it for them. Basically, we made a 3D model of a very substantial portion of Uppsala, and then deployed the traffic simulation and pedestrians and bikers and, you know, ideally we'll do lots of other aspects. But basically, they were, in this particular study, they were interested in studying the trams and how it would feel. So this is just to give you an idea, and there's the 4D really means, 4 means the time, the simulation, the things moving, the animations moving along. All right, there's lots of more videos, and this is just one of them. Let me come back here. All right, so let me explain to you what's involved in doing simulations in general. And then I'll tell you what's involved in doing very large scale simulations, which is the kind of simulations that we are doing here. So, so simulations in general are very interesting systems that, you know, there's a whole course on simulations that people can give. But basically, it amounts to having a bunch of persistent objects that change state over time. It's basically an iterative process. And then there's many types of simulations. I'm not even going there. So there's event-based simulations, there are time-discrete simulations, there's all sorts of things. But the ones that we are doing here are basically time-discrete. It's time-step. At every time step, the state updates, so things change. You know, cars move places, pedestrians move places, etc. Then, besides the simulation itself, which happens sort of in a sort of unembodied server side somewhere, there's also the visualization part, which is different. Okay, visualization is a different component that comes in and connects to these servers, and then you see, that's what I showed you. Okay, there's a visualizer, which in the case of this system is a client-server architecture. You have the server side that does all the simulation, and then you have the client that actually visualizes what's going on. So that's sort of what's going on in here. And there's messages going from the servers to the clients and the clients to the servers because it's interactive visualization and lots of interest. It's really, really interesting, okay, from an engineering perspective. Now, when you go and do a very large-scale simulation, like the ones that we're doing here, so the Uppsala model is a model that encompasses a slice of Uppsala that is 1.5 kilometers by 3 kilometers. Okay, so this is very large. There's lots of buildings, lots of roads, and there can potentially be a lot of detail because we want to do, we want to simulate all the way from a bird's eye view to details, details of the station, architectural details and whatnot. So because it's very large, one of the problems is that it doesn't fit in one server. It just doesn't fit. So you either have to go and do this in a very large computer, or else what people do usually when things don't fit is that you just have a grid of servers, and then you divide things somehow, okay? And this is the part that starts going into modularity. You divide things. Now the question is, how do you divide it, right? So you have a large load, and when you go into talking to parallel computing and stuff, you talk about workloads. So you have a large workload. Now, there are many ways of slicing things up. Okay? So the more traditional way in this community, and especially in massive multi-user online environments, the more traditional way of slicing things up is what's called space partitioning. Okay, so space partitioning, the space is your unit of primary decomposition. So you have 3 kilometers by 1.5 kilometers, so what you do is that you divide that virtual space into a grid, and you give each slice of the space to a server, right? That's what's being done here. And each of these servers does essentially exactly the same thing, okay? They simulate whatever objects are here, and they send messages to whatever clients are connected here. So basically, they are clones of each other. They just simulate whatever objects happen to be here, okay? So that's sort of the state of the art in massive sort of multi-user online environments that want to support very large maps. There's different ways of doing this, and certain companies do it slightly different, but this is sort of the traditional way of doing it. So what that means is that, for example, if I'm simulating traffic, and I have a car that's in this region here, okay, this part of the map, and the car is moving, and at some point the car moves to a space that is simulated by another server, there's sort of a handoff, there's a migration of this object from this server. There's a little packet that goes from this server to that server saying, hey, there's the car, it's going to your space, so I'm handing it off to you. Okay, so that's, again, this is all being done. This is what you do when you do space partitioning. And this is also what we started doing with this company, okay, when the first version of the traffic simulation did this. Now, this was quite a challenge. There are many problems that come into this, and here's some of them. Some of them are minor, but one of them was really the killer, okay? And so the two first ones are minor. Basically, whenever there's migration across the border, there's sort of a visual quirk, because it takes time for the car to get there, the other side. So you could actually see the cars kind of traversing the borders. It was not pretty. And when you have many cars, you could see many, kind of the hiccups going around. There was the occasional overload while the modelers are modeling, because this is actually an environment where the modelers can put the 3D models in there, so you can log into this environment, and many people can log into the environment. So by having the traffic going on at the same time, if the traffic was very heavy, or if the modelers were doing something that was heavy, it would interfere, with the load would interfere. And those are actually what I consider to be minor problems. The bigger problem is actually the fact that there's no separation of concerns. Okay? This is something that you probably know what I'm talking about. Now, the separation of concerns here, I'm not talking about abstract separation of concerns. A very concrete problem, okay? A very concrete pedestrian problem is that I'm the one doing the traffic simulation, right? And there are always bugs and improvements to make. So every time that there's something wrong and I need to fix something, I needed to kick all the modelers out. I had to shut down the server, kick them out, deploy a new DLL, and 2 hours later they could come back to work. And even if it was only half an hour, it was there was enough of a disruption that it was really getting on the way of the workflow. So this is a very tangible consequence of the lack of separation of concerns. Okay? People are being prevented from working because you have to shut down the server, because everything is mushed together, right? So this was what finally kind of prompted me to, it was really getting in the way. It was a major problem in terms of the workflow. So this kind of prompted me to think, okay, fine, let's do something different, okay? So a different approach, let's really think about all these aspects as if they are aspects, right? So the traffic simulation is an aspect of the urban environment that you're developing, just like the 3D buildings are in the modeling that the modelers do is another aspect. So let's actually separate them, okay? So separate the traffic simulator from the world simulators, and eventually other aspects will be separated too. And basically this avoids all the previous problems, okay? And let me start by the rosy, the nice part of the story. So this is great. And we move to this, okay? So here's how things look like now. The way that this looks now is that I have a bunch of servers over here that simulate the space, the map. This is where the modelers work. These are servers here, and the modelers connect here, and they do their work here. And then somewhere on the side, I have another server that the only thing that this server does is simulate traffic for the entire area, right? So this thing is just a traffic simulator. Now, the interesting thing is that, so these servers don't know anything about these cars, okay? It's just like, it's separation of concerns, okay? These just serve the world, and these cars are yet an overlay, an aspect that's placed on top of, these servers don't know anything about it. But the way that it works is that it's the viewer, okay? It's the visualizer that connects to all of this together. And the visualizer kind of combines all the data from all the servers and makes the whole coherent story, right? It's an illusion. When the user connects, there's an illusion that things are all in the same space, but in fact they are, but the different aspects of the space are being simulated by different servers. And the data is coming from these different servers. Okay, so this is the ultimate aspect-oriented separation. Okay, it works great. Up to a certain point, right? Now, you can't really have the cake and eat it too, so there's problems. There's new problems. These are new problems. They're not the old problems. The old problems have been solved. So with aspect modularization, it's great because now the modelers just, I don't need to stop them. Every time that I need to change something on the traffic simulation, it's just that other server on the side. It's just that the traffic suddenly stops. That's great. People stop seeing cars. And then when I deploy it again, they start seeing cars again. But at least they're not disrupted. It's great. It solved the problem. So what are the new problems? New problems are related to data sharing and APIs. And let me tell you, this is a very, very ugly problem. And you probably know, because this is the part that it will all sound very familiar. So, so I have my traffic simulator over here, and I have my world over here, and I wanted to have more, like the pedestrian simulator that was on the side, and other things like, some economic aspects being simulated sort of on the side as aspects. The problem is that these things are not completely independent, right? You know that. Aspects are not completely independent. In fact, they work over the same data, essentially. Right? It's all the same cities, the same objects they need to share. So, for example, if I separate the pedestrians from the cars, and if I want to avoid the cars to go over the pedestrians, the cars need to know where the pedestrians are, and vice versa. Right? So I can't get away with the fact that these things are entangled in somehow. Right? There's data dependencies here. So if we're not careful, as you know, we end up with quite a complex set of APIs. Right? We'll have an API for every single pair of aspects. Right? So for example, the modelers might want to put some traffic lights on the world. Right? Some 3D objects that are the traffic lights. Now, if I want to add traffic lights, my traffic simulator needs to know about where the traffic lights are. Right? So I would have to have some sort of a data sharing over here. And then also over here, right? And if I add more aspects, I have this basically an n-square complexity problem in terms of dependencies that is unmanageable, right? Now, I hope that this is not you. You probably have talked about it, you've written about it in papers, sort of in abstract, because this is what happens when you separate things in aspects. It can get completely unmanageable. So, what do you do? Okay, so, and this is one of the reasons why right now the infrastructure that I have for that company only has a traffic simulator here separate. I didn't even go try to do more things because I can already see that this is really messy. And I don't want to have more mess than what I already have. So, so this is the point that you should decide to kind of stop and say, okay, let's think about it, okay? What should we do now? Clearly, this doesn't scale in terms of complexity. So what's the right thing, what's the next right thing to do? So this is what I'm going to talk about. And what I'm going to talk about involves, it's kind of a substantial piece of work. It involves many things, including language design, but I'm not going to talk much about the language design. I'm going to talk more about the architecture design, just to give you the idea. Basically, what I realized is that I need a data or / object sharing model that is a little more sane than those n-square combinations that were kind of emerging. So I need something that is not n-square. And so what I came up with is basically a bunch of things influenced by lots of things, like differential computation, which is basically the fact that we're in a simulation, a time-step simulation. Influences from tuple spaces from Linda, okay? For those of you who know what Linda is about. Relational algebra, I love relational algebra. It's a great way of describing and slicing data. Even dependent types, a little bit, for those of you who know, dependent types are another great idea. And even quantum mechanics a little bit. You'll see what the connection to quantum mechanics when I start talking about copies, replicas of things going around. So this is all going in a big pot. And let me start explaining with a picture that, again, I think you all know what I'm presenting here. So you have the traffic simulator, the pedestrian simulators, you have the viewer, and they all have to have some notion of a car, right? They all have to know about cars, but exactly what do they need to know about cars, right? Maybe actually they don't need to have the same information about cars because they're doing different things with the cars. So for example, the traffic simulator in many ways is the one that kind of owns the cars, right? So it's sort of the producer of the cars, and it knows a lot of things about cars. Position, speed, the direction, the maximum speed, maximum acceleration. It has a bunch of attributes that it needs to know about the cars. The pedestrian simulation actually doesn't need to know a lot about the cars. And in fact, there's an even more interesting variation of the pedestrian simulation that it almost doesn't need to know anything about cars. I'll tell you a little bit more. But basically, you know, it could know maybe about the position and the speed and the direction because that's what it needs to know in order to detect whether there's a collision going on and the pedestrian should stop or not. The visualizer, the viewer, maybe needs to know about the position, the speed, and rotation because it needs to interpolate. The viewer also interpolates to make the visualization nice. But then it needs a lot more other things, like what's the JPEG that you know, the 3D model, what's the mesh that you're going to use, what's the color, the shape, you know, there's lots of other things that the visualizer needs to know that nobody else really cares about. So basically, we have this idea that I think it will sound very familiar to all of you, that there's a car, and there's some essence of a car, but really what the different computation spaces need out of the car is different, right? It's not the same thing. So, and in here, what I really like to think, the way that I like to think is that there's sort of data over here. This essence of things are data, pure data. And then what you do with the data is where you come and actually the data becomes objects. Objects as in data with behavior, right? Objects are a great way to think about data with behavior. But data with behavior only exists in the context of its use. It doesn't exist in sort of at the essence. The essence is sort of amorphous. So that's the way that I like to think about it, and that's what I really want to do finally, and we're doing it. So the idea is that we end up with an architecture that is actually not new at all, in fact. So basically, it's one where you have a data store, an amorphous data store, and then you have several components that use data from the data store and do whatever they want. Now, this is a very old picture. Okay, and there's nothing new in here. Every web application is architected like this, right? You have a data store, a MySQL database on the back end, and you have a bunch of web servers that pull data in whatever queries they want to issue out of the data and just do whatever they do. So this is an old idea. And as usual, this is a great idea. And great ideas, people keep coming back to them over and over again because they are great ideas. Okay? So this is great. Now, one of the problems with this picture, and it actually is very critical with the kinds of simulation applications that I'm doing, is what happens over here. How do you pull the data from the store and how you put it back, right? And if you have been involved in any capacity in programming web applications, you know that this is ugly, right? There's all sorts of hard-coded SQL queries that you make. You know, that SQL code is usually a mess. It's like what SQL queries you make, and it's just a complete mess, very, very messy. And then there's also the mess that you query, and then you have to create objects sort of manually so that your application creates the objects. And then when you send back, you have to serialize the objects back into raw data and put it back. And this is usually done sort of at the level of the program, so the programmers do this. And so this is again, a well-known problem that people have written lots of papers about how to integrate SQL with object-oriented programming and all that. So it's not a new problem. But this is something that I kind of wanted to avoid. And so one of the things that we are doing is that we are doing a little bit of the language design that I'm just going to talk about a little bit about it here. That I'm calling it predicate collection classes. And what that means is that what I'm getting out of the store are things like subsets of the data, subsets or joins or unions or intersections or you name it, projections, the whole shebang of relational algebra. But they are basically sets of data that then get automatically incarnated in my computation space as objects. Okay, in classes that I decide what kind of classes. So in here, I'll have a car, a certain car class that makes sense for my computation, and have another car class over here that makes sense for that computation, another one over there, right, with the right methods. And what I'm pulling out of the store are sets of raw car data that get instantiated here as the right car objects. Okay, so there's a whole other paper that I'm working on to describe this language, but I'll tell you a little bit. So basically, this is inspired by this is where the inspiration to dependent types come from. And for those of you who don't know dependent types, a type is a predicate upon a dynamic value. Basically, static guarantee is about dynamic properties of the object. So you can define a type that depends on certain runtime values of the objects. Okay, that's a general idea. What we are doing is not a constructive proposition. What we are doing is basically a retrieval proposition. Basically, give me all the objects that have this property. Give me all the objects from the store, all the car objects from the store. For example, if I want active cars, okay, are the cars that, for example, have the velocity is not 0. So give me all the car objects from the store that the velocity is not 0, and by the way, instantiate them here as the type active car. Okay, so that's the kind of thing that we are doing here. Let me show you, for example, here. So active car, basically we're designing a little language as using attributes. We're doing it both in Python and C#. So this is the attribute saying a subset of car, and this is the predicate. Okay, it's a query. So get me all the cars where the velocity is not 0. Okay, and so these are all these predicates are run at some specific points, and I'll tell you when that happens. But this is what brings the data from the store into the local computation. And then at the end, I'll tell you a little bit more about that. All the changes that have been done to these cars, these active cars, get passed back to the store, right? Because you need to share among all the different components that are using the same data store. So one thing that I want to point out right now is that this is not really the kind of dependent types that you see in languages like Haskell, and it's not that, because I'm in an imperative world. So I want it so that if I have an active car, right, I'm getting an active car object, and I want to be able to change the velocity to 0. Okay? If the car reaches its destination, it stops being an active car, so I have to set its velocity to 0. And so from that point on, it stops being, it stops honoring the predicates of active car, but it's still a valid object in my application, right? The guarantees is that when I retrieve things from the store, whatever I retrieve honors the predicate that I have decided to say. So next time I go to the store to get active objects, if I had changed my active car to velocity 0 and pulled it back to the store, that car will not come back next time that I go and get active cars. Okay? So this brings to the other idea that I think is very important here, is when do these exchanges with the data store happen? Okay? And this is the part that web applications are very, very messy, because if you're not careful, if you don't impose a very strong programming style in web applications, your code can go to the data store at any time. Okay? And that is very, very messy. So what I want is to impose a certain style of interacting with the data store that is really constrained. And in the case of simulations, that's actually possible, because simulations, and actually not just simulations, but many other kinds of applications that have this property that there's a frame. There's a frame of computation, be it in a while loop or some event handler or some timer or some event handler or something. There's basically something that happens, okay, a scope, in which in the beginning you can fetch data from the store, and when it ends, you can push the data back to the store. So in the case of, so this is a generalization. In the case of my simulation, I'm in this situation, okay, so I have a timer. Every 100 milliseconds, there's a time step. So in the beginning, we pull the data from the store, and at the end, we push the data back to the store. Okay? All of the components, all of the computing components are doing this, right? Now, there's all sorts of interesting questions of the rate of change and whether, compatibility about the rate of change and all that stuff. It's all part of things that the simulation world needs to worry about, but that's sort of the basic idea. So, but the idea is that the interaction with the data store happens at very specific points in time. It's not whenever people want, okay? There's no going to the data store in the middle of this computation. It's only in the beginning and at the end. The other thing that's important is that all of these computations are independent. They don't share memory other than the data store, okay? There's no shared memory here. So whenever you pull data from the store, you actually get a copy. So if you have two components pulling car data from the store, they both get copies of the car, okay? There's no sharing. And when they pull it back to the store, if they changed it, now you have to think about what's the consistency model here, okay? That depends on the application. In the case of what we are doing, we don't really care very much. It's like the last one wins, basically. So other applications might not be that relaxed, but many applications you can be pretty relaxed about the consistency model. So basically, there's guarantees at the border that whatever you get from the data store honors the predicate, and then when you push it back, it gets reflected back to the original data. Okay? That's sort of the language. So let me show you some more examples here of how this language kind of looks like. So if you have a car, and again, it's a very explicit language design that for now we're doing, that we're saying, okay, we're almost overlaying a SQL language on top of objects here. So we're saying that all of these are dimensions, right? Dimensions as in columns, in tables, right? So here's a car, there's a pedestrian over there. We're also stating in our primary keys, just like in relational databases. And now here's some examples of what I call the predicate collection classes. So here's an example of an inactive car, which is a predicate collection class. And what it says is that it's a subset of cars. And what it gets is the cars for which the position is 0. So I decided that inactive cars are all at the 0 coordinate. And active cars are those for which the velocity is not 0. Okay, so at every tick of the simulation, all of these predicates are run. Okay, it goes to the data store and gets whatever active and inactive cars the computing node might need. And notice that these classes, these predicate collection classes, they have their own methods that might be independent from other uses of cars in other computing nodes. So in this case, here's how these active cars move in this particular component. Right? In other components, there might not even be an active car. And if there is, it might not have anything to do with this particular class. Right? So it's just that when you get the data from the store, it becomes an object with methods. So here's another interesting situation. So for example, here's a stopped pedestrian, here's a walker. Again, I'm just showing the predicates over here. The interesting one is this one. This is an interesting one. So suppose that I'll explain a little bit more. Suppose that in your pedestrian simulation that you want the pedestrians to avoid the cars. Okay? So you have to detect when the pedestrian, when the pedestrians are close enough to a car that they should stop. Okay? So there are many ways of doing that. One way might be for the pedestrian simulation, the component of the pedestrian simulation, to pull car data from the store. At every tick, you pull the positions of the cars and directions, right? And then internally you decide whether there are pedestrians that are close enough to the car. But there's an even smarter way of doing it, which is you don't even pull car data from the store. All you need to know is which ones are the pedestrians in danger. You have the concept of a pedestrian in danger. What's a pedestrian in danger? Is one that's close enough to a car. And that you can actually compute at the store. So you can give it a query to the store that says that the pedestrians in danger are those that are basically for which the distance between the car and the pedestrian is less than a certain threshold. So now the pedestrian simulation component has the concept of a pedestrian in danger object. And it's guaranteed that that pedestrian was in danger. So whatever the component that needs to do with that particular pedestrian, it knows that it's there. But the predicate is run at the store. So you don't even need to bring car data, which is great, especially if you're doing distributed simulations. Right? You want to push a lot of the computation and to some other place, and you want to bring as few data as possible across the network. So that's sort of the idea that you start thinking about these concepts that are basically predicates and subsets of the data. All right, there's more things in here about what these framed computations look like and the kinds of authority that they have over the data. Some are producers, some are only consumers, some are producers and consumers. So this has to do with reads and writes, right? Who can read and who can write. And if you annotate this enough, then you get even more guarantees that things are going to be, you cannot do optimizations, for example. So if you have a component that's just a reader, a getter of cars, then you pull data in the beginning, but you don't need to push it back. Okay, that's great. So it avoids sending data back to the store. All right, so what I'm going, so in the works is basically what I'm working right now with my students is the full relational support for this language. So basically we have subsets, we have projections, we have cross products, we're working on intersections and unions, we're working on foreign keys, by the way, that turns out to be interesting. And foreign keys in the object world is basically object references. So you have an object graph. And what that means is that when you have an object that references another object, that in terms of relational algebra, that means that there's a foreign key relation between a table and another. Okay, so we're basically doing a conversion between the relational algebra concept of foreign key and object references. So let me just show you a little demo that oh, by the way, actually I have lots of things to show you. I forgot. This stops projecting. No. Hello. Okay, so this is just to show you how I showed you the video. But I also wanted to show the environment. This is the real thing, okay? This is running. I'm connecting to the server right now. These are the cars. There's a little, as you can see, there's lots of improvements on traffic simulation. That bus was just over that car. Okay, the collision detection here is not working very perfectly. So just to give you an idea of the kind of kinds of environments that I'm talking about, and basically, just show you that this is what we have. This is where the modelers model. This is what they show to the cities, the customers that they have, and this is also the tool that we make videos to then, and kind of web offshoots that show on the web for the public to see what is going on. So this is one thing that I wanted to show you. The other thing that I also want to show you is. By the way, so this right now, the architecture that is here is the architecture where you have the model area being served by a bunch of servers and the traffic being served by another server on the side. So it's the aspect decomposition, right? And this is where I kind of stopped because I realized that it was going to be quite messy and complicated. And so the next version that we're going to have is going to have what I've been talking about here. And in order to get there, we've been prototyping these ideas of predicate collection classes in the smaller version of this. So that's what I want to show you. Let me show you a very, very small version of this. I'm actually the live code. All right, so what I'm just showing you here is a visualization of it's three aspects over a data store. The aspects are traffic simulations of cars, pedestrians, and the viewer, which is this graphical client. Okay, and these three things all use the same data store and use it use it in this way that I just explained. Right, so this is a simulation. So in the beginning, they get the data as predicate collection classes. So they do whatever they need to do, change the state, change the position and whatnot. And then at the end, it goes back to the store. So that's basically, you have three things. It's the walkers, the cars, and the viewer. The viewer is a separate thing too. There's some visual quirks here too. Come on. So at the point that the car gets there, did you see that? So that is the point at which in the pedestrian simulation, that data is identified as a pedestrian in danger. Right? So as a pedestrian in danger, in my pedestrian simulation, there are provisions for what to do with pedestrians in danger, with instances of pedestrians in danger. Okay, so we're kind of prototyping this over these simplified models of the real urban simulation. So there's walkers, there's pedestrians. We're experimenting with language, current pedestrian. There's a pedestrian in there. I don't know if you can see. Probably can't see. But here's the class pedestrian in danger. And that's the query over here that I was showing you that I have in the presentation. Okay, so let me kind of wrap up here. All right, so aspects are great in terms of separation of concerns. You know, it really solves the problem of the workflow that we had. They bring new problems, and this is the potentially n-squared complexity that we really don't want to go there, really. So in order to avoid this, the way that I'm going at it is to go back to this old architecture, which is to have a data store that all the components share. But in order to facilitate this, what I want is to be very strict about when to interact with the data store and how. And I want to interact semantically with the data store. I want the data to suddenly be given a soul, right? The raw data that does not have a behavior, I want it to have a behavior and embodiment in each of these different things, the different embodiments. Okay, and then sent back again. So basically, this is a data-driven API. And I'm doing it with this concept of predicate collection classes. And this, I think, is going to solve all my problems. So it's going to support aspect decompositions, which are great, and it's going to avoid the n-squared complexity of APIs. So I actually have a course now that I'm going to start in 2 weeks on distributed urban simulations, in which I'm going to attempt to do this with 25 students. What we're going to do is that I'm going to serve a model area, and each of the students is going to group them in two, so there are going to be about 12 aspects. There will be students doing fleets of Uber cars, doing fleets of normal cars, doing fleets of Amazon trucks. I'm just going to focus on traffic because it's the simplest one. So different kinds of traffic. And they're all going to do this. Okay? The only thing that they're going to know about each other is the data model. Then they will know that they will be able to pick up data from the others. And they need to actually one interesting thing is what kinds of communication mechanisms, human communication mechanisms need to be in place in order for them to know that the Uber car, like what does the Uber car look like, right? And what can I pull from the Uber car? So that's going to be sort of an interesting experiment that's going to happen here. But hopefully, ask me again in June, but hopefully this will work. I think it's going to be really, really cool. All right, so concluding remarks. Architectural separation of concerns, I think it's a real need in this domain when you go for large simulations, because with large comes the fact that it doesn't fit, and the fact that it doesn't fit, you need some sort of a decomposition, and there's many. So how do you decompose it? What's the right way of decomposing it? The right way depends on many things, including what is it that you want to optimize. So in my particular case, the workflow of people working is really important. And this is actually not just my case. I could tell you a war story of this thing called the high-level architecture. Has anyone heard about the high-level architecture? I thought you might. So the high-level architecture was something that was designed by the Department of Defense, by the military. It's a very heavy top-down kind of standard. It's actually an IEEE standard. And it was prompted precisely because the military, you have lots of simulation environments and lots of different contractors. They needed an architecture in place to be able to kind of have all these contractors and these different aspects of these environments being able to kind of coexist. Okay? So it was exactly this problem that they had, that they have all these contractors, each one, you know, one is doing the tanks, the other one's doing aircraft, the other one's doing pieces of the tanks, you know, all sorts of different things, and they needed a way to kind of weave everything together. And they put together a standard, the high-level architecture that everybody hates. It's like nobody uses it. It's super complicated. Nobody knows what to do. It is basically an event-based architecture. And again, as you might know, event-based architectures are great, except that if you don't give people guidance for how to use them, they're equally messy. There's, again, an n-square problem of events and hidden dependencies. It's a complete mess. So you need to give people these guidances and these constraints about how to use things, and that's sort of what I'm shooting with, a much more strict kind of programming style that gets at the same problem. And that programming style is the idea that there's an amorphous data store that gets polymorphic data uses. The idea is that there's this identity. So objects have identity. Data has identity. That's important. And they get copied, and while they are being used in all these different applications, they are isolated. So there's data isolation. So basically, there's replication, and this is where quantum computing comes into mind, right? So there's many instances of the same car in the different processing units in here, right? And that's okay. Eventually, the data gets back to the data store, and the data store has sort of the ground truth for what the car is at any given point in time. Yeah, and I think this basically goes into this informal way that the urban simulation people think about their problem, and that's exactly what I'm doing. I want to be able to support these different aspects and simulate them in relative isolation from each other, but of course with the data dependencies that are completely unavoidable. That's about it. I'll be happy to answer questions. Oh my God. Yeah?
Normally people think of the city as a static element, but
a what?
A static that doesn't evolve. But it's not true. Normally they evolve for changing for the layout. I'm just thinking about new buildings, new streets, but also not planned changes like, for example, accidents or blackouts that close areas and stuff like that. So I'm wondering how, if you do, and how do you consider the evolution of your simulation?
That's a great question. That's a great question. It goes to one of the problems that we discuss in this company, which is version control.
Oh, yeah.
Right? We need version control. And in fact, you can see that already in this Uppsala model that I showed you with the trams going around. The trams don't actually exist. That was an experiment, a study that the city wanted to do, and I'm not even sure if I'm going to deploy the trams. So now we're actually doing another project with the city of Uppsala that is supposed to be as what it is now. So we have to remove the trams out of there, right? So we basically need to go back in time to a point in the model where the trams didn't exist. But so that is basically, you know, we already have solutions for that. It's called Git, source control, right? So it's just a matter of kind of putting all these things together and you know, cities are live. They change all the time. Urban planners are always doing experimenting with different ideas, and some of them go through, some of them don't go through, stay only in the virtual world, and that's exactly the kinds of activities that I think should be supported by a simulation environment. It's not, you know, it's not making a simulation, it's not the end of it. It's just the beginning of the conversation. And that's exactly the position that this company is taking.
So following up on the idea of change, so I've worked in this area as well. If you are using visualizations in a participatory context where you're asking people their opinions, they will often say, well, what if we put the tram one block over, or what if we moved it there? So ideally what you like to do is just go type, 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 and have the new simulation show up on the spot. Are you there, or
Yeah.
can it be, can you, what kinds of changes can you make, and how fast can you make them?
Yes, so there are certain changes here. We're getting there. So this environment supports live editing of things, certain things. Certain things the modelers can do. Other things the modelers need my help because so for example, traffic simulation, if you want to reroute things at this point, I need to be involved. Hopefully we'll develop tooling that it would actually, the modelers would be able to kind of reroute the traffic, but we're not there yet. But what they can do is that, you know, if, and actually that happened already, that the people that they were showing the model to realize that one of the buildings were too short. And if, actually that had implications with respect to the shadows. So another thing that you can see here is the shadows. So that, you know, that was a very easy fix. The modelers could do that on the spot, just increase the size of the scale of the building, and that was done. So there's definitely that need for very rapid iteration of these models for people to really see, you know, very fast what it will take.
Thanks a lot. I very much enjoyed your talk. It's just more a thought. I was, you know, when you described the problem, I see that there's a theme of synchronization or data synchronization is also part of that. There's this concept of lenses which can take, let's say, a central data store and help you synchronize views with the central data store, or maybe separate databases. Right? So the view update problem. And there's also various works where people looked how to integrate that into programming languages. And I see that there might be actually some interesting connection since you're looking at sort of semantic queries. And I could imagine that there might be a need for some of these agents to actually have local stores. Because they might be specialized, and then basically you're going to have some local models, and then you have the big somewhere federated, and you need to synchronize these.
Yep.
So the notion of lenses, update lenses, there's lenses with uncertainty that actually push constraints.
Right.
So that's how constraints also could be integrated.
Right.
I wonder whether you have any thoughts on that.
Yeah. Let me just, I don't know if that goes into what you were saying, but there's very much, when a component gets data from the store, it can do whatever it wants with that data. Okay. The only sort of constraint is that in the beginning of the frame, it gets the data, and at the end of the frame, if it's a writer, then the data gets pushed back automatically back to the store. But whatever the application does here with the data, this is full imperative programming. You know, you can store it elsewhere, you can change it, you can do whatever you want, basically. And in fact, so for example, the visualizer is a very concrete example. What I showed you, these 2D little walkers and cars going against each other. The viewer itself, it's a graphical viewer. So the simulation that's not the viewer is happening at a rate of 100 millisecond tick. Okay, so it's like 10 per second. That is very slow for visualization. So when you have a graphical client, you want to render it much faster than that. So the visualizer is actually ticking much faster than the data gets updated. Okay? So what's happening is that the visualizer is doing its own interpolation of the data. So it's changing the cars, it's simulating basically, it's moving the cars itself, right? Independent of the owner of the cars is doing. And then it just happens that the viewer is just a reader, so it doesn't send anything back. And so when it goes back after a certain time, it gets the authoritative position of the cars. And that's why you see those quirks sometimes, because I didn't really do a good job of synchronizing things very well. But those are all the interesting things that come about synchronization of the data. Oh yeah, but I see that as something that emerges on top of this architecture. So talk about emergent behavior, all sorts of emergent behavior with graphic simulation. And especially when you have some bugs in there, whether it's a bug or a feature is a different story, but many times there are unintended consequences of certain decisions. So many times I've ended up with gigantic traffic jams, right, that I had not anticipated because there was some, the threshold, for example, for the lookup of, there's an angle that I see the cars for detecting collisions. And if the angles are too large, they're being too, they're just trying to detect collisions with lots of things. And so sometimes the cars would stop even though they would not need to stop. And because they stopped, there would be a pile-up of cars, So there's all sorts of emergent behavior. But I see that sort of as a more in the A-life kind of work, things that emerge. But I think that the architecture here is I think that's what's really important. And then it allows people to study all those kinds of emergent behaviors and whether they are bugs or features. And that's the interesting question.
Yeah, the issue is, should we represent that explicitly?
No.
So
No.
like
Right.
If I may ask, with respect to different perspectives on classes that you displayed here regarding the car class, or object, but I think you apply this all throughout, or intend to apply this all throughout your application. Isn't this a move towards symmetric aspect-oriented decomposition that was advised by HyperJ that didn't come to the point that Aspect J came to real application development?
I don't need Aspect J for doing any of this.
Yeah, but isn't this you pointed out that separation of concerns based on asymmetric aspect-oriented view, which is present in Aspect J, like having advice and base, and advising the base code isn't viable. And you showed us that a viable solution would be to decompose by different perspectives and having different versions of classes. This was something that was presented at least as a prototype and idea in IBM's research on their prototype with HyperJ language. Are you familiar with that?
So, as I said, these are all ideas that have been floating around for a long time, okay? I'm not really particular about the semantic definition of a symmetric versus symmetric. I'm sorry, I lost track of all that. But the idea here is that what you were talking about, what's base and what's not base, I don't think that I even had that in my non-data store aspect decomposition. I think that I had dependencies going all over. It's not like the model was the base, right? It was like they were all bases of each other because they need to know data about each other, right? So that was already there. It's unavoidable. So yeah.
I have a last question.
Yeah.
Yes, I didn't see very clear how do you model the context.
The what?
The context. By context, I mean the unexpected event that may happen during the execution of the system in the real world. I mean, for instance, if part of the city there is a blackout or the traffic light was part of the city are down, or simply the weather condition, your car will perhaps use a different collision detection algorithm if the weather condition change. So how do you represent this adaptability in your system?
That's a great question. I'm not entirely sure I understand that question, but there's lots of versions of that question that are really interesting. So one of the versions is what happens if I have pedestrians and traffic and some other aspects over here, and then this server suddenly goes kaput, right? So it crashes. Now, what happens to the data that was the authority of this server, right? Ideally, we would like all the others to kind of know that this data now doesn't exist anymore. Otherwise, otherwise what will happen right now, right, in my little prototype, is that if the cars go away, if the car simulation goes away, the car data is still in the store, but nobody's changing it. So what happens is that the pedestrian simulation go get the car data, and the cars are basically stopped all in the same spot, right? So we need to have a mechanism to detect that the owner of certain data went away, and maybe that data needs also to get garbage collected from the store, right? That's an interesting problem to have, and I don't have that problem fixed. And there's another version of your question of related to connecting so hybrid systems. So basically have a simulation that is also partly getting data from the real world, right? So this is actually a project that we're doing now, the second project that we're doing with Uppsala, in which they want to visualize buses going around the city, and they put some sensors on the buses to detect some air pollution of some sort, and so they want to visualize that. So we need to inject basically this other data stream into the system that's actually from a component with real data. But I don't see that as fundamentally different. It's basically a different kind of data stream, and the data goes into the store. And whoever needs that data uses that data. But so it fits with this model really well. It's just a different kind of component that brings more data to the store.
Yes, but the question is more or less the second one. We are working with Siobhan Clark from the Trinity College of Dublin in mixed traffic, where you have the autonomous cars, and then you also have those cars with drivers.
Right.
And the weather, we are injecting different behavior depending on the weather condition, depending on the environment, depending on the content that under simulation we can control, that in real world we cannot control. And this is the idea. But I know that this is new in the simulation area.
Right. So, but the idea here is that in this architecture, I think it's really valuable for all those kinds of hybrid models, right? That you basically have this concept of the data store, and you have these components that put data in the data store, and others that use data, their own and other components' data, and each component is free to do whatever they want with the data that they get from the store.
That's very interesting. So thank you, Crista.
Thank you.